It's so tiring working on this laptop and sheets for several hours. तो क्यों ना थोड़ा म्यूजिक के साथ माइंड को रिफ्रेश करें because work has to go on, show must go on. This looks good. जी सर, yes sir.
मेरी एक प्रॉब्लम फंसी हुई है, थोड़ा सा आप अगर इसको रोक लेंगे तो मुझे लगता है कि मैं थोड़ा सा
you are super intelligent sir. You can go with music also sir. थोड़ी देर just cooperate for some time.
अरे सर ये तो गड़बड़ कर दिया आपने.
Sir please sir because I have some very important tasks to complete and I was really getting sir just for some time sir. Just for some time sir.
सर कुछ इलाज करना पड़ेगा इसका तो.
सर आपने मेरा फोन चुरा लिया. सर वेयर इज माय फोन. सर ये स्किन टेप. सर आप पढ़ते पढ़ते स्किन टेप पे आ गए. ओह माय गॉड सर आई शुड गिव अप नाउ बिकॉज़ ये स्किन टेप है एंड ये स्किन इफेक्ट के सामने तो आई डोंट नो द ब्लूटूथ इज गोइंग टू बी डिस्टॉर्टेड और मेरे पास आई ओनली हैव ब्लूटूथ. काश मेरे पास शायद अभी ब्लूटूथ ईयरपीस वाले ब्लूटूथ होते तो सर मेरे म्यूजिक को इंटरप्ट नहीं कर पाते. तो सर लेट अस टॉक अबाउट दिस. मुझे लगता है सर थोड़ा स्टूडेंट्स को बताते हैं व्हाट एग्जैक्टली दिस स्किन इफेक्ट इज. व्हाट डू यू से सर?
जरूर सर जरूर.
एंड सर इसको बताने के पहले लेट अस आल्सो डेमोंस्ट्रेट द सेम थिंग कि इफ वी प्लेस द मोबाइल इनसाइड अ डाइलेक्ट्रिक
में ये इफेक्ट हमें नहीं देखने को
मिलेगा. कर लेते. लेट मी सर्च अ डाइलेक्ट्रिक एंड ब्रिंग इट इन फ्रंट.
बिल्कुल चेक करते हैं और बल्कि इसको एक्सप्लेन भी करते हैं.
तो सर देखिए अब ये गाना वापस बज रहा है. इसको हम डाइलेक्ट्रिक में चेक करते हैं और जब ये एयर टाइट है, दिस इज कंप्लीटली एयर टाइट. लेट अस सी व्हाट हैपेंस. स्टूडेंट्स प्लीज हैव अ लुक.
इस पे कोई असर नहीं हो रहा.
कोई असर नहीं. एब्सोल्युटली नो ब्लॉकेज. यस दिस म्यूजिक इज स्टिल रनिंग. वो वहां पे एकदम बिल्कुल बजे जा रहा है. राइट. सो guys what phenomena is this? Ashu sir what is this happening? And can we do one more thing? इसने कंडक्टर ने क्यों फ्रीक्वेंसी को ब्रेक किया, डाइलेक्ट्रिक ने क्यों नहीं किया, वो तो एक्सप्लेन करेंगे. लेकिन आपने जैसा मेरा फोन यहाँ पे प्लेस किया एंड इट वाज डिस्कनेक्टेड फ्रॉम ब्लूटूथ. व्हाट विल हैपन इफ आई पुट माय फोन एंड यू ट्राई कॉलिंग मी?
तो भी एग्जैक्टली सेम मेरे हिसाब से सेम फिनोमेना.
चलिए वो भी ट्राई कर लेते हैं. मैं अपने फोन को यहाँ पे प्लेस कर रहा हूँ.
मैं आपको
अगेंस्ट कंडक्टर
इसको लेकिन थोड़ा ज्यादा इस बार मुझे लग रहा है प्रेस करना पड़ेगा क्योंकि स्ट्रेंथ यहाँ पे सिग्नल की काफी
अच्छी है. तो सर आप ट्राई कीजिए कॉल करना.
तो मैं कॉल करता हूँ और मैं स्पीकर पे इसको लगाता हूँ सो दैट हम देख सकें कि पेनिट्रेट हो रहा है कि नहीं हो रहा है. तो मैंने इसको स्टार्ट किया है. मैं कॉल कर रहा हूँ.
पुट इट ऑन स्पीकर. हां कीजिए सर.
तो ये कॉल नहीं लग रही है इसमें क्योंकि सिग्नल पेनिट्रेट नहीं कर पा रहा है. अब अगर मान
सर एक बार काट दीजिए इसको. स्टूडेंट्स यू हैव सीन दैट देयर इज नो कॉल कनेक्टेड एंड ऐसा नहीं कि मेरा फोन एयरप्लेन मोड पे हो. वी आर नॉट चीटिंग यू. नाउ हैव अ लुक. सी माय सिग्नल स्ट्रेंथ 6 cc. It has gone zero and now it has come. Even the Wi-Fi went zero because Wi-Fi also works at a frequency of 2.4 GHz which is pretty much similar to the frequency of Bluetooth. राइट.
तो देखिए सर इसमें मुझे लगता है कि स्किन इफेक्ट ने पूरा बढ़िया से काम किया क्योंकि ये हमारा जो है एल्यूमिनियम का है और इसकी जो विड्थ है वो भी काफी मोटी है.
कंसिडरेबल है.
एंड इसको भी अगर आप देखेंगे तो ये भी स्टील का है बट ये भी काफी मोटा है. तो हुआ ये है कि हाई फ्रीक्वेंसी की वजह से ये सिग्नल जो है इसमें पेनिट्रेट नहीं कर पाएगा. तो इस वजह से एक काइंड ऑफ आइसोलेशन बन गया है. तो बाकी इसको जो है ना प्रॉपर्ली तो मुझे लगता है कि हमें स्टूडियो में एक्सप्लेन करना चाहिए.
कोई नहीं सर दौड़ के ऊपर जाते हैं. और गाइस स्टे ट्यून्ड. लेट अस गो टू द स्टूडियो एंड लेट अस explain with equations ki what's skin effective, how electromagnetic waves cannot propagate inside a conductor but also it can propagate inside the dielectric. ठीक है, दोनों का डिफरेंस समझते हैं. Tuning to the studio.
So guys, so already as you saw the experiment related to the skin effect, now let us come to the equations and the ideology behind that. Why the Bluetooth connection from the mobile was interrupted when the mobile phone was placed in the aluminum container which is a good conductor. At the same time, when the same mobile phone connected with the same Bluetooth operating at the frequency of 2.4 gigahertz, when placed in the plastic container which is basically like a dielectric, there was no disconnection. Okay, so you know guys, there's a lot of things behind wave theory and the equations. Okay, and you know there's several steps involved in finally deriving the wave equations, but in this small video I'll give you a brief overview of that and I'll focus more on the skin effect part. So this is just to give you an overview that you know the wave discussions, the wave propagation theory basically starts with the final equations, the final ideas of the Maxwell's equation equation, and Maxwell's equation also, you know, one by one turn up when you start from electrostats, magnetostat, time varying fields. You study Gauss law, Ampere's law, Faraday's law of electromagnetic induction. You study the concept of magnetic monopoles being present or not. Okay, so you accordingly get Maxwell's equation. Now guys, from these Maxwell's equation, we derive the wave equation commonly known as the Helmholtz wave equation, which in the 3D form is given by del square Es equal to gamma square Es, similar for the magnetic field. Now what is gamma? We'll have a talk about that as well. Del square is the Laplacian operator. Now assuming that the wave is traveling only in one single direction, let's keep it simple in the beginning. Assuming that the wave is traveling in a single direction, and let that single direction be z. It could be x or y also, but let that single direction be z. Then this Helmholtz equation in one dimension basically simplifies to del 2 Es by del z square equal to gamma square Es. Now which is nothing but a differential equation for us. Okay, a linear differential equation for us, which we can solve by the concept of CF, the complementary function. There will not be even PI required in this case. Okay, so everybody can solve the differential equation. Let us solve and see what is the final solution of wave equation after solving the differential equation, and that turns out to be Es, which is the phasor form. That turns out to be E naught e raised to the power minus gamma z AE, right? AE, this has to be AE hat. Okay, so AE is the unit vector along the direction of electric field. So if the wave is traveling in Z direction, electric field could be in X direction or Y direction, because we all know that electromagnetic waves are TEM in nature when they are traveling in the free space or unbounded medium, and TEM wave means the electric and magnetic field are both transverse to the direction of propagation of wave. Actually, their directions are also related by the fundamental AE cross AH equal to AK, where AK is the DOP. Like here, the direction of propagation is the Z direction. It could be anything in general. Okay, now talking about this very important factor gamma, which is known as the propagation constant, and that turns out to be root over j omega mu into sigma plus j omega epsilon, and because it is the under root of complex numbers, it is also expressed as a complex quantity alpha plus j beta. Here omega is the frequency of the wave, sigma, the very important parameter, represents the conductivity of the medium, and this has a role to play. Now I will classify accordingly, you know, conductors and dielectric properties. Okay, mu is the magnetic permeability, epsilon is the electric permittivity, as we all know. Okay, now dear, here alpha, the real and imaginary parts respectively, alpha and beta. Alpha is known as the attenuation constant, and this is important for us for understanding the skin effect. Alpha is the attenuation constant. Why so? I will going to explain that. Okay, which is expressed in Nepper per meter or also in decibel per meter if you take it in the log scale, and beta is known as the phase constant, okay, which is measured in radian per meter. Okay, now the final time varying forms. The previous one was the phasor form. Now what is the final time varying forms of the magnetic field? So there is a procedure to convert phasor to time varying forms, that all you will study. Let us come for this. This is important for you now. The electric field finally in the time varying fold is given by E naught e power minus alpha z cos omega t minus beta z AE, where AE is again the unit vector along the direction of electric field. Now look into this part. This is basically looking like a cos theta function for you. Okay, and in the a cos theta, what is the amplitude? Similarly, we have derived the magnitude of magnetic field, but I'm just picking up one of these components, either electric field or magnetic field, to explain you this theory. So in this a cos theta form, dear, what is the a? What is the amplitude of the wave? Okay, the amplitude part is simply here E naught e raised to the power minus alpha z, and let me use my pen here, because we all know that e power minus alpha z or e power minus ax is a form of exponentially decreasing function. So when I talk about the plot of this particular amplitude function, yes dear, when I talk about the plot of this particular amplitude function, the amplitude as a function of z, it is E naught e raised to the power minus alpha z. Okay, that means when I take it at z equal to 0, it is having the amplitude E naught, e power 0 would be 1, but e power minus alpha z represents exponentially decreasing function. So as the wave travel, amplitude is going to decrease. It simply represents that for every inch the wave travels in the medium, it is going to lose its amplitude. Even it is attenuating, eventually it loses the power, the total power contained within it. So as the wave travels, it loses power. Okay. Now, the amplitude is an exponential function at the end of the day, given by e power minus alpha z factor. Let us define one parameter, that a particular distance, let us say that particular distance is delta. Okay, let us say the particular distance is delta. What happens at the particular distance which is equal to delta? So if I put z equal to delta, what is the amplitude? the amplitude becomes E naught e raised to the power minus alpha delta. Okay, so I am calculating a distance which is traveled by the wave such that its amplitude becomes the first exponential factor of the original amplitude. So what is the first exponential factor? E power minus 1. So E naught will get cancelled, comparing both the exponential power. So we get alpha into delta equal to 1, and the value of this distance, delta, is simply equal to 1 by alpha. So let me come here. Okay, there is a distance at which the amplitude becomes E naught E inverse. Acha, E inverse आप निकालोगे ना, so that is approximately 0.37, 37%. Okay, so let's say this is 37% mark and this is the distance delta. So there is a distance, okay, which the wave travels such that its amplitude attenuates by first exponential factor, and that depth, that distance is going to be called as the skin depth. That is going to be called as the skin depth. Okay, we'll have official definitions related to it. That is going to be known as the skin depth. Okay, it's mentioned in front of you. So as the wave travels in a conducting medium, as I clearly explained you, its amplitude is attenuated by the factor e power minus alpha z. Now the distance delta through which the wave amplitude decreases by the factor of E inverse, which is approximately 37%, that is known as the skin depth, or also known as depth of penetration, or simply penetration depth, because it is a measure of how deep a wave can penetrate inside a medium. Kitna deep ja sakta hai inside any particular medium. Right? Now, the plastic container you saw, okay, was basically a lossless dielectric. So not lossless, but yeah, let me first tell you lossless. We can apply this theory for any good dielectric as well. So what is a lossless dielectric? Which is characterized by zero conductivity, opposite of conductor. Conductor has high conductivity, dielectric is opposite of that, and that is having sigma equal to 0. Now, what I'm going to do, let us start with the formula of gamma, as we already noticed, and in this we are going to put down this sigma equal to 0. So when you put this sigma equal to 0, of course, what is the relation you get? J omega mu into j omega epsilon get multiplied, and eventually j omega square outside the under root. So you have gamma is equal to j omega root mu epsilon. Gamma, okay, is equal to j omega root mu epsilon, and when you compare it with alpha plus j beta, gamma should be alpha plus j beta. So what is the real part? Sir, 0. What is the imaginary part? Omega root mu epsilon. Now this beta also has a several important, to related with the phase of the wave, related with the velocity of the wave. But right now amplitude and attenuation and skin effect is the topic of this moment. So eventually, dear, alpha is equal to 0. And what happens if the alpha is 0? What happens? We have obtained alpha is equal to 0, and hence amplitude, which was E naught e raised to the power minus alpha z, because of this alpha 0, e power 0 is 1, and here there is a wave, there is this idealistic wave, because I have taken the ideal dielectric, whose amplitude is nothing but just representing a constant value, whose amplitude is representing a flat line. Its amplitude never attenuates. So however wave that travels, जितना भी distance travel करना है कर लीजिए, but amplitude कभी reduce नहीं होगा. This can also be understood by taking the skin depth. What was the skin depth formula? The skin depth formula was 1 by alpha. Okay, and because alpha is 0, 1 by alpha tending to infinity. Now what was the skin depth? The distance traveled by the wave, so that the amplitude reduces to 37%. How much distance? Infinite. Matlab, when will the amplitude reduce to 37%? Never. It's like never. And that is why in perfect dielectrics, okay, that is why we also call it as lossless dielectric, because there is no losses, there is no attenuation. Okay, the wave can travel any extent without suffering any loss. Okay, although, we cannot say that, you can find materials with sigma equal to 0, but yeah, even if you talk about good dielectrics having low conductivities, right, having low conductivities, the alpha would be very low and skin depth will be very high. The wave can penetrate to a comfortable distance within a medium, within a dielectric medium. But on the other side, let us come to the good conductor. So if I specifically talk about good conductors, they are characterized by conductivity which is very high. For perfect conductors, which is an ideal situation, sigma is tending to infinity. Okay, now very common good conductors that you must be knowing. Okay, very simply, copper, sigma is in the range of 5.8, 10 raised to the power 7 Siemens per meter. 10 power 7 ka range. Or let's talk about why not aluminum. We performed the experiment using the aluminum, na? Even for aluminum, the conductivity is somewhere approximately 3.5 into 10 raised to the power 7 Siemens per meter. So look at these materials, or even for gold, silver, these are all very good conductors. Okay, so we can say conductivity is not very high, it's actually very, very high. And now what happens due to the sigma being very high? Okay, I hope you are able to realize how high these values are. So what happens when this sigma is really very high? So the sigma is much greater than this factor omega epsilon. Why? Epsilon will be in the range of 10 power minus 12. Omega, even if you take gigahertz frequency, like we are talking about this Bluetooth frequency and all, omega 10 power 9, epsilon 10 power minus 12, still omega epsilon, when you multiply it, is a small number, very small number in front of sigma, which is 10 power 7. This is 10 power minus 3 minus 2 range mein aayega. Okay, considering these facts, sigma is much greater than omega epsilon, and that is why this term is approximately neglected. Okay, and we get the gamma approximately j omega mu into sigma ka under root. Solving it under root of j, solving by basic complex numbers, which you can all do, dear. Okay, we get this expression for gamma 1 plus j root over pi f mu sigma, and when you compare it with alpha plus j beta, so common aa gaya, so alpha beta is common here, and the alpha and beta combinedly are given by the equation root over pi f mu sigma. But mere liye important abhi alpha hai na, sir. Okay, so alpha and beta root pi f mu sigma. Alpha is root over of pi f mu sigma. So for high sigma, okay, for sigma is very high, the alpha is also very high. Number 1 point, the alpha is also very high. Okay, theek hai. Acha, if I talk about the perfect case, if I talk about the perfect conductor, what is going to happen? Sigma tending to infinity. So of course, under root of infinity is infinity. Alpha also tending to infinity. Alpha tending to infinity, the amplitude which is given by E naught, e power minus alpha z, e power minus infinity, we all know is 0. So what is the amplitude of the wave? Kuch hai nahi, baba. The amplitude of the wave is 0. That means the wave has simply vanished away. Okay, for how much distance? Irrespective of the distance. Distance kitna hi chota kyun na ho, alpha itna bada hai that the amplitude is 0. That means whenever the wave strikes a perfect conductor, okay, whenever a wave strikes a perfect conductor, या अगर आप good conductor भी ले लोगे तब भी कोई harm नहीं है theory में. Okay, alpha is going to be very high, and that is why the skin depth will be very low, because they are inversely proportional. So if I first assume a perfect conductor, whenever a wave strikes a perfect conductor, its amplitude vanishes away, and that is why the skin depth 1 upon alpha will be 0. So how many inches, how many centimeters a wave is able to travel in a perfect conductor? Absolutely nothing. So it can only travel along the surface of conductor, but it cannot penetrate inside it. It cannot penetrate inside it. What about a good conductor? Yeah, of course, good conductors, delta, the skin depth is not really 0, but it's very small, just like very few, just like centimeters. And also it depends, if you take the frequency range to be very high, okay, like we were talking about in the range of gigahertz. So even the alpha depends on high frequency. Alpha high, already sigma is high, f is high, alpha will be extremely high, and then the delta will be very small. So wave travels only few negligible centimeters inside a good conductor. It mostly attenuates, and it only travels surrounding the conductor, touching what? Okay, like say this is the conductor, it cannot penetrate. This is not conductor, but मान सकते हैं ना? It cannot penetrate inside, but it can travel along the surface. What is this? This is skin. It can only travel along the skin of that surface, and that is the fundamental phenomena you know by the name of skin effect. Because in conductors, the primary transmission of energy will take place in a region outside the conductor. In a region outside the conductor, because all time varying fields attenuate very quickly within a good conductor. Okay, the fields attenuate very quickly within a good conductor. Okay, all fields in a good conductor are essentially 0 at distances greater than few skin depth. Okay, electromagnetic energy is not transmitted in the interior of a good conductor. It travels in the region surrounding the conductor. Okay, it travels in a region surrounding the conductor, and that is what is the phenomena known as the skin effect. In very brief, I have tried to cover it. Okay, I hope this video arouses your interest in EMFT. in your concept of skin effect, so that you go back and learn, sir, what are the Maxwell's equation, what is Gauss law, what is Ampere's law. You have to start from the fundamental, how Maxwell's equation come, how do we then come to Helmholtz equation, how to solve Helmholtz equation, more. But yeah, through a small experiment, at least the idea of this series, that is a Sunday special Learn with Fun, through small concepts to arouse your interest in engineering, in GATE, so that eventually somehow, you just stay motivated. So guys, this is the first Learn with Fun video on the BYJU'S Exam Prep ECEECS YouTube channel. Hope you liked it. If you really liked it, do not forget to like the video, so that we all get to know how much interest you are showing. Also, at the same time, if you want to watch more such videos, subscribe our channel, because many videos other than this also is live videos are going on, post GATE sessions are going on, but every Sunday Learn with Fun coming up. So subscribe the channel so that you don't miss any video. Also, at the same time, very important request, because this is the first video of the series Learn with Fun, and we are keeping it every Sunday. Next Sunday I'm going to bring you next video, which is going to talk about RFID technology. Yes, RFID being used in corporate buildings, in corporate locks, in hotels, in fast tags, you can say, or used in parking management systems, in malls, several places. RFID technology is useful. Why it is useful, how it is useful, what is that RFID technology. Next Sunday I'm going to explain you and cover a video on that. So stay subscribed, and very important thing I'm mentioning you, please mention in the comment box how you like this video, whether it arises interest in you or not. Okay, if you like, if you're motivated, then we will try to increase the frequency of such experimental based video. So guys, all those humble requests, all those watching the video, whatever your opinion is, do mention in the comment box. If you don't like, mention you didn't like, okay, but mention something so that we get honest feedback about all the efforts that we are making. With this, I, Rakesh, signing off. Bye bye, thank you, stay safe and take care of yourself.